Good afternoon, and thank you for sharing your lunchtime with us. We're very grateful to those online, to those who are watching live. Thank you for coming. Now, today, Eva is going to present on how policy interventions can make e-fuels or alternative fuels for decarbonizing shipping and aviation cost competitive or cost effective. And I'd like to just introduce her. She's an alumni. She studied MSc in Environmental Technology. She was one of the students that worked on this project. Her MSc project was on aviation, especially looking at PtL. She is currently an analyst in carbon limiting technologies, and they're focusing on accelerating transition to clean solutions across both public and private sectors. She has acquired experience in public sector policy in Australia. And interestingly, she has a BSc in neuroscience. So her quantitative skills are very great. Now, this is a joint project by three students, so Eva, T, and Shifa. So Shifa worked on shipping, T worked on aviation, but advanced SAF, advanced sustainable aviation fuels, and then Eva on PtL. So I'll just start introducing the work my group does because they worked with my group during the summer G Lab, and then I will sit down, you will take over. So a lot of the work we do is focused on how to make decarbonization solutions cost effective, and we look at those decarbonization solutions for heavy sectors, so iron and steel, cement, chemicals, refineries, petrochemical, shipping, and aviation. Those sectors are responsible for 31% of global carbon emissions. And we explore how market-based interventions can improve their economic viability. Now, there are a number of challenges with deploying these solutions, technical, infrastructural, skills, but we're majorly focused on the economic challenge as a group. Now, what we do is we've discovered that there is a gap between the price of a sustainable solution or a clean solution and the business as usual. And no matter what you do on the engineering side in terms of improving the performance, finding better catalysts, finding better ways to separate or capture CO2, there's still that gap. So exhausting engineering innovations has not led to shortening that gap. So what we do is to say, what can we do with external interventions? What can we do with market-based policies to support the price reduction of sustainable solutions, whether they're incentives or grants? What can we do with private finance to bring down that cost from a bottom-up level? And if we still don't get to a point, that economic tipping point where it becomes cost competitive in business as usual, what do we do with other interventions with electricity markets, but also how do we penalize the business as usual, carbon heavy solutions to get to that economic tipping point? And we do this analysis for all alternative fuels and technologies required to decarbonize energy intensive sectors. And we've shown through several case studies that market-based interventions can reduce costs and generate that demand pool to trigger for that cost reduction until we get to that economic tipping point so we can make decarbonization a reality. Now, Eva is going to focus on shipping and aviation, and I'll take my seat now. Thank you for coming.
Yes, thank you so much, Femi. And Femi has been absolutely fantastic as a supervisor last year. And as a woman in clean tech, it's very inspiring to see. So thank you so much for inviting me back. I'm very happy to be here. And thank you to those of you who've come in person for your lunch and those online as well. I appreciate you taking the time to come along. And yeah, my background, as Femi said, I did a BSc in neuroscience. Kind of took a bit of a convergence, and then I joined the Master's in Environmental Technology, where I met Femi and started researching aviation fuels in my thesis term, looking more specifically at power to liquid e-fuels. And yeah, I'm now working up in Trafalgar Square at a company called Carbon Limiting Technologies, and we focus on a lot of kind of commercialization, looking at sectors like CCUS, cement, kind of hard to abate. So very much continuing on this work now as well. And just first of all, like a question for the audience. do you think that aviation and shipping sectors need financial support for decarbonisation? It'd be interesting to know what the perspectives going into this are, because we kind of debate whether it should come from industry funding or government funding. Yes?
I think it's
Yeah, kind of sharing the burden load is what we kind of looked at through these models, which is quite interesting. Does anyone else have any kind of, Alex?
That's my big conception. Too expensive to get to the point where it's actually viable, but I know nothing, so I'm looking to it.
It is expensive, you're correct, but we'll get into that. So yes, without further ado. So just in general, the kind of the pathways to decarbonisation for both aviation and shipping kind of come from policy, finance, to technology. And you have this kind of convergence of technological breakthroughs, public finance, market-based mechanisms, and then also kind of some private finance market shaping mechanisms. I'm looking at these specifically for shipping and aviation. You get things like the EU ETS for shipping. You get kind of improvements in global fuel standards. You have kind of more private finance mechanisms like the Poseidon principles. And for aviation, you have obviously all sustainable aviation fuels. You have the international CORSIA, the UK ETS, the SAF mandate in the UK, and then you have more private finance mechanisms like offtake agreements. And just to give an overview of what we'll kind of jump into today, just some general background first of all, then kind of looking sector specific, shipping and aviation. I'll give a kind of high level overview of the methodologies used in all of this analysis. Then we'll look at 3 case studies and then some conclusions. And it's just worth noting that, as Bemi said, this work is from a couple of our projects all kind of merged together. So one of the case studies is mine, and 2 others are Shifa and Teens. So firstly, just some background on shipping. We all know that shipping is a huge part of the global economy, facilitating 80% of global trade by volume, which is huge, and contributing 3% of global greenhouse gas emissions. But this is projected to increase to almost 10% if we continue on the business as usual scenario. And this might be due to kind of more stringent regulations in aviation at the moment, which might push more goods to be transported via shipping. And why does shipping face such a huge decarbonisation challenge? Well, it's a couple of reasons, but primarily it's a very energy intensive industry, huge energy demands, long haul ship lifespans, which makes it quite hard to have any kind of fleet improvements. I think the average lifespan can be 20 to 30 years, which makes it very difficult to bring in novel fuels and kind of infrastructure changes on board. Additionally, it's a competitive landscape and they operate at very tight margins. So it's kind of difficult to incentivize the shipping side to kind of get on board with alternative fuel types. And there is just a general lack of scalable, economically viable alternatives like green ammonia, hydrogen, or electrification. And we can see just here on the right-hand side that this is just kind of an overview of the efficiency improvements that kind of can emerge in shipping, and it's estimated that around 80 to 100% of that can possibly come from hydrogen and other synthetic fuels, e-fuels, which is quite promising. And then looking at aviation, in the UK, the climate impact of aviation is actually higher than other countries. It's around 8% of total emissions in the UK. So definitely a very pressing issue looking at policies going forward. And aviation contributes around 20 billion to annual UK GDP, so it's very important and it's not going anywhere, I would say. So, and again, very important because it transports so many of our high value pharmaceuticals and food products that are very time sensitive. Around £6 billion worth of those. And demand for commercial and aviation is projected to double by 2050 under the business as usual scenario. So we definitely need to do something to address these kind of increasing emissions and to try and decarbonize the sector. But why it's so challenging is, as we know, aircraft has weight and size constraints, which make electrification very difficult. Batteries would be too heavy, so it's not as possible. We all probably know from our most recent Ryanair or Jetway flight that the refueling times are very, very short. So it makes it very difficult to kind of bring infrastructure change at the actual aircraft level. And there's quite a lot of regulations around fuel type. Fuels have to be high density propulsion fuels. So it makes it difficult to kind of meet the Jet A1 standards with other fuel types. And this is all calculated as per the UK SAF mandate. So from 2025 to 2040, there's a set of legally binding targets for fuel producers to have a certain percentage of their fuel being sustainable aviation fuel. So it starts off pretty low in 2025, which is the year the mandate's coming online. So 2% for all SAF, and then specifically for e-fuels or power to liquid fuels, it's 0.2%. And it kind of gradually increases up to 2040, where it's 22% for all SAF types and 3.5% for power to liquid e-fuels. So it's still quite negligible in some ways, but we're getting there. And you can kind of argue that the EU mandate is a lot higher. And I spoke to some Department of Transport kind of policymakers whilst doing this research, and they kind of advise it's better to set targets that are more attainable, meet them, and then push it upwards rather than the other way around. And I guess, why are e-fuels so promising for these industries? I'm not sure how many of you have prior experience with e-fuels or power to liquid fuels, but it's worth kind of looking at the diagram on the right-hand side, noting that e-fuels are a scalable drop-in and that can be used as an alternative to fossil fuels. And the biggest advantage is that they can kind of fit into current infrastructure. And most critically, they are produced using renewable electricity, water, and captured CO2. So on this graph or kind of diagram on the right-hand side, you can see that carbon is captured via direct air capture, combined with hydrogen that's produced via renewable electricity, synthesized into kind of a combined fuel that can then be dropped in up to like a 50% blend with conventional kerosene and used for transport or for shipping. And so, yeah, just reiterating, for shipping, it's quite advantageous, high energy density for long haul routes. You can drive decarbonisation without too much modification to the vessels. Also, it's very easily bunkered at ports, which is quite a big kind of benefit. And for aviation, it can be blended with Jet A1 and used in current infrastructure. And it's far more suitable than the electrification solutions for long haul flights. And I guess it's worth caveating that while Bemi and I have looked into the kind of financial, economic barriers, and all of the modelling, and this is kind of addressing those challenges, there are far more challenges facing both industries today. So whilst in the financial kind of barrier, there is the high investment costs and long payback, high capex, a weakened competitive edge from kind of policy uncertainty. There's also a lot of regulatory barriers that come from that direct policy uncertainty and kind of giving a reduced incentive to invest in alternative fuels. There's a lot of regulatory risks and there's a lot of market fragmentation, which is what we've kind of seen at the moment with biofuels seem to be kind of driving forward, but some of the other fuel types have kind of been left behind. There's quite a few technical challenges, so supply chain challenges, a lack of scale technologies, infrastructure constraints. Then within industries, there's obviously some conservative approaches to decarbonisation, to indirect pressure from stakeholders, from investors, and then some level of lobbying. And although we have these incredible solutions, it's also difficult to get the workforce kind of lined up to meet those and get everyone trained up. So yeah, to kind of achieve long-term decarbonisation, it won't just be the financial, which is what we'll be speaking about today. It will be primarily a mix of all of these coordinated together. And just some kind of sector progress. So this is a projection from the IEA, kind of showing the projected energy consumption in exajoules, both for current years and also for future years. So the red is obviously all very bad, fossil fuel makeup of the fuels, but you can see that gradually for shipping in 2040, we get more ammonia coming online, more biofuels coming online, small amounts of methanol, and then some electricity-based fuels. And then on the right-hand side, similar for aviation, it's very fossil fuel-based until 2030. Then 2040, it starts kind of driving upwards, getting biofuels online, and then synthetic kerosene tends to kind of become a huge, bigger part of the constituent mix. And looking at these graphs, it's worth addressing the kind of questions, and this is where a lot of the analysis that BEMI's lab group does is kind of how effective are policy mechanisms at ensuring that this low carbon mix in the 2040-2050 year group is achieved? What is the best mix of policy instruments? Is it better to use incentives or is it better to use penalties? And are existing interventions sufficient as of today? So just a high-level overview of the methodology. So all of the modeling in the case studies was based on kind of optimization modeling. So you have an objective function, which could be to lower cost for government or split the cost between 50-50 industry and government. You have a number of constraints, like the strike price for fuel can't be greater than the selling price. And then you can kind of mix in a number of decision variables into this to give a kind of bottom-up analysis. And that kind of allows you to ask some questions of how effective are interventions in generating sufficient demand pull to trigger technology cost reduction? How can we balance these to supply push and demand pull efforts? And then one key thing in these analyses is when can a tipping point be achieved? What is the year when alternative fuels will cost the same as conventional kerosene? Can we use policy intervention to bring that tipping point closer? And this is an overview of the kind of policies we'll be diving into today. I'm sure you're all very familiar with them, but just in case. So carbon tax and emissions trading schemes, which kind of provide financial incentive to switch to alternative fuel types. Then kind of subsidization, so using direct subsidies to lower the high upfront costs for either stakeholders in shipping or in aviation. Contracts for difference, so kind of finding a guaranteed strike price. So fuel producers will get a guaranteed revenue regardless of the market outcome. Carbon contracts for difference, sorry, which is just a kind of more novel iteration of the general contracts for difference, but just uses the carbon market price and kind of stabilizes that. So for every ton of carbon a fuel producer sequesters, they will get a guaranteed revenue back from that. And then kerosene taxation, just trying to make fossil-based fuels less competitive on the market by introducing a slight kerosene tax. And in case there's any economists in the audience, this is why I added this in case anyone wants to see the kind of objective function driving the graphs, etc., that it will come up. So yeah, this is kind of just the net mitigation cost objective function, but I won't go into too much detail, but if anyone wants to ask at the end. But yeah, these equations can be kind of applied to a mix of subsidies, carbon taxes, and ETS schemes, and they kind of allow you to determine the optimal policy mix to achieve price parity between fossil fuels and between the alternative fuel type, kind of by simulating temporal price changes. And then I focus more on the aviation model. So these are my equations. So happy to take any questions, but again, allowing that kind of optimal policy intervention mix to be determined. So this is the contracts for difference equation, and then the carbon contracts for difference scheme. And I was kind of comparing the overall price of both of those to government and industry. How much would it cost to underwrite each? What would the most viable strike price be across all scenarios? And then for the kerosene tax, similar, basing it off total UK jet fuel demand as per the SAF mandate, and kind of just playing around with that with different levels of kerosene tax. So this is the first case study, which is low carbon fuel mix and global shipping. And this is done by Shifa. And firstly, just kind of looking at the IRENA projections for future fuel uptake in the sector. And again, it's very dominated by HFO, MGO, with minimal kind of alternative fuels coming online in 2030. But by 2040, there's quite a big shift in the mix where you can see e-ammonia is making up quite a large constituent of that. And then by 2050, e-methanol also comes online as well. So there is definitely demand, future projection demand there for those fuel types. So we kind of looked at, basing off that previous graph, what is the actual demand for e-ammonia and for e-methanol? And it's actually pretty substantial at around 3.5 exajoules for e-ammonia and about 0.85 exajoules for e-methanol. And you can just see that, unfortunately, the price of both of these fuels, so for e-ammonia, it's around $200 per tonne currently, which is very expensive compared to the kind of HFO alternative or conventional pathway. So you can see that even the best case scenario, the prices don't achieve parity until 2039, 2040. And similarly for e-methanol, kind of same trend is seen slightly earlier because it seems to kind of decline faster, but yeah, price parity isn't achieved until kind of end of 2030s. And it goes back to this question of how can market-based policy interventions actually trigger these economic tipping points? As Bemi showed this graph earlier, you know, kind of bringing down that cost whilst using policy to kind of bridge the tipping point a bit faster. And these are some of the outcomes of that analysis and shipping. So using today's carbon tax values around the world, only around less than 20% of the market share can be achieved. So what this kind of means is that our analysis showed that to drive decarbonisation in shipping, the carbon price would need to be around $400 per tonne, which is quite unrealistic in a sense when it's currently at around $100 per tonne. So definitely need policy intervention for both e-ammonia and e-methanol to kind of bridge that gap. We'll just sit there. And yeah, so carbon taxes alone are insufficient, they're not enough. So you need a kind of balanced blend of policies. So what the most optimal policy outcome was in this case was a mix of carbon taxes that were kind of peaking at around $160 per tonne, then ETS pricing that kind of stays around $160 per tonne, and then subsidies that kind of stay consistent at about $60 per tonne. And those three policies kind of interact to drive decarbonisation forward with e-ammonia. And then again, looking at e-methanol, very similar carbon price of around $125 per tonne, ETS pricing of around $70 per tonne, and a subsidy staying steady at around 50 megawatt hours. And just some summaries from case study 1. So decarbonising the shipping sector does require substantial financial investments with market-based policies like carbon taxes, ETS allowances and subsidies. But unless they kind of interact carefully together and we have the correct balance of each, they're insufficient to drive kind of widespread adoption of these cleaner technologies. And without intervention, e-fuels may not be competitive before 2039. So you saw in that original graph that the price parity was achieved very late on, but it kind of comes forward when you kind of find the correct policy blend. So yeah, combining demand pull policies will enhance effectiveness compared to standalone approaches. And just in general, this approach to kind of identifying the optimum policy was quite novel. It was one of the first kind of models to do so, particularly looking at the phased reduction of free allowances under the EU ETS. It's been very infrequently done where you look at that kind of the perfect policy blend to try and determine what drives decarbonisation. And the second case study then is looking at more generally at CFDs, so contracts for difference for advanced staff in UK aviation. And I guess it's worth noting that this is for advanced staff rather than e-fuels in particular, but very relevant because it kind of drives forward the underpinning analysis for case study 3. So what are the role for CFD schemes in the UK? Well, they can reduce the cost gap between advanced sustainable aviation fuels, which we definitely need to decarbonise, and fossil-based fuel in the UK aviation sector. And you can see this graph on the right-hand side that the price of all advanced SAF is huge, at around £3,500 pounds per tonne. And obviously kerosene is around £800 per tonne, so there's a huge price differential there that needs to be addressed. And under the business as usual scenario, the price of e-fuels doesn't come down until around 2044, 2045, which is arguably much too late. So how do CfD schemes work? Does anyone know how CfD schemes work or have any kind of experience with CfDs? Exactly. Yeah, so you can see here from this graph on the left that the blue line is the fuel price, the green dotted line is the strike price. If the market price goes below the strike price, government will pay into the CfD, and if the market price actually goes above the strike price, industry or whoever the counterbody is will pay back into the CfD. So it's quite a good way for government to be able to provide upfront funding for something novel like e-fuels, and also kind of guarantee that revenue certainty for producers, but it should kind of have a combined effect of bringing new investment into e-fuels. And this is what we kind of mapped out in this case study. So in the kind of positive section of the graph, funds are flowing back to government. And when it's negative, funds are flowing back to industry. So it's kind of just a oscillating relationship between government and industry. And primarily government does tend to underwrite the schemes, but that's something we explored in the analysis as well. Who is best suited to underwrite these schemes? And yes, you can kind of see here in all of these graphs, without an intervention like a CfD scheme, there's a huge shortfall in meeting the mandate. So you can see in the black dotted line is the mandate level, and everything in grey is the shortfall. So these are kind of a couple of different scenarios. I know the SAF mandate has some upper to lower limits of kind of how much fuel they want produced, what the percentages are. So in case you're wondering why it looks like the same thing, it's just different scenarios. And yeah, just main message is there's huge shortfalls without any policy intervention, and we're kind of way off the mark, especially in the kind of scenario C, the shortfall is huge. And then this is kind of what happens whenever a CfD is brought in. The shortfall is almost gone, and we're meeting the mandate levels consistently, and achieving our decarbonisation targets. Just a summary from case study 2. So a strike price of around $800 to $1,000 per tonne of SAF is needed for financial feasibility, which when you look at kind of PtL e-fuels where it's about £6,000 per tonne to produce, there, yeah, a huge differential that needs to be kind of overcome. By 2040, a CfD-backed SAF could achieve price parity with kerosene and reduce kind of government support needed by around 30%. And a well-defined exit strategy kind of ensures gradual subsidy reduction. So we kind of played around with seeing what year you can kind of constrain the model to say, you know, by 2040, the funds have to be split between government and industry 50-50, or you can kind of play around with that. And we found that that was the best kind of outcome. And then in terms of what always comes up with CfDs is, well, who's going to fund it? Well, government won't underwrite it, industry won't underwrite it. So Tian, who did this case study, also considered some kind of funding options. So looking into the revenue generated from the UK emissions trading scheme. And she found that that would actually cover around 70% of the required CfD funding. And air passenger duty, she also found that that would kind of plug in that remaining 30% gap and would also target the polluter. And then case study 3, which was my own case study. So I was looking at contracts for difference and carbon contracts for different schemes to meet the UK's e-fuel PtL mandate. And again, just kind of showing this contracts for difference versus carbon contracts for difference. The only main difference here is that with the regular CfD, the strike price is based on the kind of PtL selling price. But with the CCfD, the strike price is based around a carbon price. And yeah, it's kind of looking at ways to balance the cost between government and industry, how to do so to kind of accelerate the uptake of power to liquid e-fuels. And yeah, high e-fuel costs do trigger revenue uncertainty, and that's probably the biggest issue in this sector, is that nobody is willing to invest whenever there's so much uncertainty around the high fuel costs. It costs, I think, in the realms of 20 million, 30 million to build a power to liquid e-fuel plant, so very expensive. If you look here, you can see that the fuel price for e-fuels starts at around £6,000 per tonne, whereas conventional kerosene is around £800 per tonne. So plugging in that gap is very difficult, and under business as usual, it's still not achieved by 2055. And if you're looking at the right-hand side, again, shows a similar trend, but for e-fuels produced via industrial point source. So yeah, this analysis is divided into direct air capture and industrial point source. So e-fuels can be made with carbon captured from a direct air capture plant, but also can be captured in industry point source, which is a lot cheaper, and is why the price for IPS PtL is around £4,000 per tonne, but still very expensive. And these graphs up here, sorry, I know that it's a lot of graphs and they're all popping up quite fast, but I'll go through the top line first. So looking at kind of DAC PtL and how a CfD scheme kind of bridges that gap a lot faster. So you can see that the strike price is set at around £4,000 per tonne initially, and then that kind of brings forward that price parity. And you can see towards the end of 2052, 2054, price parity is achieved. But of course, when you look at the corresponding plot below, it shows the spread of government industry payments, and government is having to provide a lot of upfront revenue. So that is definitely a challenge. But once industry gets on their feet, they can then pay back into that. And very similar trend for the industrial point source carbon-based power to liquids. They're just a little bit cheaper because the carbon's coming from waste industries, so it's a bit easier to kind of plug that gap. And kind of price parity is actually achieved by about 2040, so it's quite significant. And government can pay less, and they can rely on industry a little bit faster, which is very promising. And then this is the CCfD scheme, so where you're basing the strike price only off the market carbon price and kind of providing a guaranteed carbon price to a fuel producer, so they'll be guaranteed to get back, £400 per tonne for every fuel shipment they provide. And you can see on the right-hand side, again, price parity is achieved a little bit faster than it would have been without the policy. And government pays quite a lot less with the CCfD, so the CCfD might actually be more favourable to government. And then looking on the right-hand side, again with industrial point source PtL, it's a bit cheaper, so it's just it comes ahead a little bit earlier, and government can pay a little bit less. So yeah, IPS PtL achieves cost parity with conventional fuels a lot earlier than DAC PtL, so it's definitely something for government members to consider. There is a regulation on how much carbon you can take from point source. I think by 2030 they're trying to phase that out totally, but it's a lot cheaper for them to actually consider using point source. And then the third scenario I looked at was kerosene taxation as an enabler for adoption within a CfD. So combining a CfD with a slight kerosene tax. So I think the scenarios I varied were around 8p per litre. So that was the kind of mid-range scenario, and looking at the revenue that would generate and how it would impact the CfD. So you can see on the two upper graphs, on the left-hand side is the CfD where there's no kerosene tax applied. And yeah, the price differential never converges. But on the right-hand side, whenever there is a kerosene tax applied, I think this is about 8p per litre, you can see that the e-fuel becomes much more cost competitive at around 2040. And of course, it actually reduces the amount the government has to pay into the CfD. So if there is a slight kerosene tax applied, it is cheaper for government in the long run. Industry gets on their feet faster, the government pays less into the CfD or the CCfD. what I also did was some kind of stakeholder analysis, because of course it's easy to plug all of these things into a model and forget that it's a real world out there with many challenges. So I spoke to some industry experts from the Department of Transport, from DESNES, spoke to some kind of individuals on the fuel procurement side. And they had some quite interesting kind of preferences for the contract for difference versus the carbon contract for difference. The majority preferring the CfD because it's a bit safer. It's been done for the renewables sector and been very effective with that. So there's kind of a lot of grounds for using that as evidence. A very few favoured the CCfD, but there's some more kind of nuanced insights on the next slide. So quite a few, which is very interesting, said that, well, the CCfD using carbon as the kind of strike price is actually more beneficial to climate and to society. So in the long term, that is definitely the more viable option. But for now, the CFD is faster and easier to implement alternative fuels. Either scheme will, of course, be difficult to administer a strike price when something like e-fuels, they're so difficult to set the market bench price for, etc. The CCfD, one of the main advantages is that it actually monetizes emissions reduction, so accelerating e-fuel uptake, and would be very in line with the SAF mandate. Going back to that kind of who would fund the contract, who would underwrite these contracts, or any policy for that matter, a lot of them will face resistance and lobbying, particularly a kerosene tax, which I definitely noted that came up quite a lot in these interviews, that although a kerosene tax is needed, it's very unrealistic and the cost may need to be absorbed by passenger airfares. And with any tax you bring in, it also risks like tankering, and it could affect some of the already pre-existing air service agreements we have with other countries. One suggestion, which quite interesting, is to ring fence air passenger duty for funding e-fuels and SAF, because in the UK there's quite a big issue with hypothecation constraints, where you can't reattribute to the same industry. And then just kind of more general perceptions that come up was that most stakeholders agreed without policy intervention, there will be no way for e-fuels to compete against fossil fuels. It's just, as you've seen with all of the graphs, the price differential is massive. It's just never going to be possible. And maybe this is untrue, but the SAF mandate and e-fuel buyout mechanisms alone will not be enough to get past the production bottleneck. So kind of making that case again for needing all of the policies mentioned in this kind of analysis, both the CFD, the CCfD, carbon taxes, ETS allowances, etc. And just some kind of overall conclusions from each case study. So market-based policies like CFDs and CCfDs do reduce the cost gaps, and they do make sustainable fuels compete against fossil fuel alternatives. And they seem to be the only way to kind of bridge that gap and gradually bring the price down and incentivize investment into cleaner alternative fuel types. And carbon taxes, subsidies, and emissions trading schemes do incentivize investment, and they do drive e-fuel adoption while reducing reliance on public funding. So the better the mix of policies that we have, the less the government has to fund and underwrite all of these schemes, all of these policies. And that's where a lot of the risk can be mitigated against, is by having the correct blend of policies. And overall, optimized policy mixes do lower production costs, and they provide price stability, and they also provide revenue certainty to both producers of the fuel, but also to investors who might kind of drive that forward and provide a financially viable pathway for low carbon aviation and shipping fuels. And yes, thank you so much. That is all of us who have the work has been contributed by. Obviously just Becky and myself here today, but yeah, a huge thank you to the other members of the team as well. But yeah, thank you all for listening, and any questions would be very welcome.
Question?
Got one?
I'm Jamie for some questions because she is the expert. Yes.
I'll go first. Horrible question. But how likely do you think any of this actually is to materialize? How likely is a market-based policy? What's the chance that it's going to be implemented?
I think the SAF mandate is good and it's going in the right direction. Potentially for shipping, it could be good to have something similar. I do notice that there's a lot, not as many legally binding targets. So I think it is that kind of legally binding. It's not really that what the buyout price. The issue with the SAF mandate is the buyout price is about £5,000 per tonne. So there is a concern that many fuel producers will just use the buyout and not to meet their mandate kind of quotas. Yeah, I don't think that anything about me, but I think we're on the right path, but definitely not a lot more work needed. And there's definitely a disjoint between kind of analysis here and what's actually implemented in policy, and there's a lot more bottlenecks. Identifying those optimal policies, testing them a lot more robustly, and then seeing whether that would translate into policy.
Also, the other side of the coin is to be able to tell how far policies will get us there, because IRENA and we have this pathway to predict what we need to, the quantities, right, to get to net zero. And they're currently the UK has the UK ETS, there's some pricing around the world, so we can show where we can students, just 20% fuels, 5% fuels. And then we can use that to calculate what our impacts on the environment will be if driven by this. But if we want to be better, then it's about increasing their values or offering just to get that demand, make it technology cost competitive. It's not going to continue forever in a good design.
Thank you. Yeah, that was really interesting and very relevant to me because I work for an NGO called Opportunity Green, and we run the Sasha Coalition, which is a group of ambitious shipping and aviation companies that are looking for green management policy. I have two questions actually, if that's all right. The first is, what are your views on the UK's revenue support mechanism and sort of how? Obviously it's open to all SAF, but do you think there's possibility for it just to be for those e-fuels, just to really make sure that that price is brought down? Second question is, obviously direct air capture is very expensive, so are you sort of doing any analysis on how to bring that price down as well?
Very interesting. I think one other project in Bemi's lab was related to DAC specifically and seeing, how the price of that can come down. So Bemi has far more insights on that than I would. But in terms of the revenue certainty mechanism, it would almost seem more practical if we have two separate, because it's not really fair to put e-fuels where the price per tonne is £6,000 per tonne in the same kind of consideration as biofuels are a lot cheaper. Both very important, but it could be good to have maybe some gradated kind of revenue certainty mechanisms to definitely bring e-fuels up, because they have been somewhat kind of in the past few years where they're very difficult to fund the projects to get kind of large scale hydrogen. I've also got issues with, should aviation be entitled to all of that green hydrogen, go elsewhere? Is there better so there are a lot of issues with that, and the revenue way to kind of overcome.
Thank you.
I don't know if anyone wants to touch on the DAC question.
Yeah, so we conducted similar studies on direct air capture and hydrogen as well, to bring down the price and what the role of market-based interventions are, because one of the bottlenecks e-fuels is the CO2 and hydrogen. I'm happy to share the videos because we shared it in some of the seminars on what we've done in that area for the in the US. It's technology, so because they're all in interested together. Now it's divided and come.
How do you link the strike prices of the CCfD, carbon reduction incentives, for instance, with the UK ETS, ETS, or with Corsia? How do you link that?
UK ETS is what we primarily used. Corsia at the moment is much too low, unfortunately. It's just not going to hit any of the decarbonisation targets. So we primarily use the UK ETS and just a couple of different scenarios, like a there are some estimations on the I think it's on the Department of Transport. You can get the best case to worst of what the projected UK ETS prices were. So we fed that into the model to try and see what the optimal strike price would be to kind of meet the e-fuel targets as per the mandate. That's anything else.
The concept of the CCfD was born because carbon prices under the EU ETS are too low. So there is a mitigation cost associated with it pathway, and there is a carbon price that has been set. So the CCfD scheme is supposed to bridge that gap. So we use the carbon price under the UK ETS, but we also benchmark against the real carbon price required to make it more competitive. And then the goal is to see how that changes with time and how much government needs to pay to cover that gap for industry to have a business case to invest. And over the time in the model, we try to balance the cost between government and industry, because it was looking as if government was going to pay out, because there is a gap, a huge gap between the UK ETS price and the mitigation cost of power to liquids. So we said over time, how do you balance that gap and generate a demand poolers to align with the UK's mandates in fields?
I just had a question. Were you just looking at UK production, or was it global production? Just because, like, with difference in cost of, say, electricity, which is, huge demands for DAC and e-fuels. Like, yeah, I'd just be interested to know that.
So the analysis is primarily based on costs for the UK, but we did look at other countries and kind of and also looked some parts of the UK are much cheaper to produce electricity. Europe's a good bit cheaper than the UK, so that does definitely, the £6,000 per tonne is only covering the UK. There's some other countries where the projections are quite a lot cheaper, but it's very difficult to model. If you're importing certain things, it's difficult to have that in the model in a level of certainty, because it brings of a challenge. So it'd be very interesting to do this with different countries, but I guess you want to have, if you're going to switch to e-fuels, you want to make sure that you have the kind of domestic supply to meet the mandate. So I think that was the kind of thinking behind it.
The shipping case study was global, where we looked at the spread of cost for e-ammonia and e-methanol around the world, and that's why we have that area plot. The UK was primarily focused on production in the UK, but we looked at the plot again was from low, like 1,900, if you get cheap electricity from 8,000. So we considered all the ranges possible. So the question is, can the policies work for anything that happens in the future?
Yeah, I was just wondering whether it would be worth looking at market interventions, like, for example, I mean, not in all cases it will work, but aviation versus other means of transportation, like terrestrial, because I'm just thinking that if the price has to be up anyway by market interventions, as you showed in your graphs, that it always goes up, I would say that there is reluctance from government to impose carbon taxes, because that will go directly, as you said, to the final consumer. So that means that in any case scenario, consumers will be paying more. And I don't see that being something, very cheered by government, because it would be unpopular, basically. So is there any other way that, maybe looking at terrestrial transportation or other market mechanisms might help, if not in aviation, maybe other means of transport?
Yeah, that's a good. That's the big concern, is who someone has to pay for using, I guess, and that's the failure pays principle. It would be worth looking elsewhere, but it did seem, when I did the stakeholder interviews, the key concern was who pays, and if that kind of government or industry pays, it's going to be passed on to consumers somehow. And yeah, I never got to the end of how to mitigate against that, but that is something that would be very interesting. But maybe I mean, if you have any.
I think the answer to your question is probably a value of across the value chain intervention strategy. Right? So the cost to producers is very high compared to the cost to end users because you have 1 billion people flying compared to 4 people who are manufacturing the fields. So there is a need to look at along the value chain and see where the critical intervention points are. How do you support end users? Will it go up to the manufacturers, the producers? In this analysis, we focused on the producers, but there are other market-based interventions and not just invested centric. But all you need is a very good demand signal because when they scale with that demand, they benefit from contribution. So that strong demand signal can come from market-based intervention for the producers, or it can come from interventions on the consumer side. As long as there is a strong demand for a long time, then they have a good business case to produce.
I just ask, when you did your surveys, did you speak to some shipping companies, whether they were questioning the impact of new regulations like from the IMO?
Mine was primarily focused on stakeholders in aviation and like fuel procurement side. I'm not sure if anyone's spoken to.
No,
it would be very interesting.
Stakeholder engagement for shipping.
In terms of policy, did you explore any other alternatives which are already in place in US? There is something like low carbon fuel standard, which is an intensity-based program. But of just focusing on this particular technology, they just leave the market to it. Was any attempt done to?
For the US, we consider the 45Q, the California Low Carbon Fuel Standards, which applies to DAC and methanol. So there's a separate study where we looked at US policies, and US is looking really good. Hopefully, Trump wouldn't add it to his executive orders, but if it remains business as usual, that's a really good demand. Even for direct air capture as well, because you can stack up the carrots, you can stack up the LSS together with the incentive for share and the incentive and you get to $200 per tonne as a good incentive for direct air capture and producing e-fuels as well.
Yeah. There's another question about the surveys you did with the aviation industry. I noticed that they were all more or less in favour of determining the strike price by negotiation in the auction. I'm guessing that's because they would like to set the price rather than having to bid for it. But is there any other reason why that might be the case?
I think again, from seeing like all of these kind of graphs and that, it's very difficult to. Although modeling is, the best way to explore and see, it's actually difficult to determine with 100% certainty that that's the best strike price. There's so many other variables that come into it, especially on the kind of fuel procurement side. They might face unknown costs, but also a lot of them, I think the issue is a lot of fuel developers nowadays are at different kind of CRL levels. So you have some in the startup phase, and you have some huge oil and gas companies that are now kind of diversifying to aviation fuel. So how can you set a strike price that kind of equally gives level playing field to all of the kind of innovators in the space? That came up quite a lot as a theme. So
just to comment on that, I think the government said that they're going to do like private law contracts within a guaranteed strike price, and then it's like determined on the individual project, and that takes into like the differences in technology, and so it can be like competitive within. Yeah.
Sounds like a good solution with strike price problem, because we don't want what happened with offshore wind last year to happen again. But what we can do is just to show from a bottom-up perspective what the value with the support government is planning And so what if we at least tick those, at least tick fundamentally who on the right? Because we're looking at 8,000 per tonne here.
Like a lot of work setting a strike price for every different project.
There's
Yeah.
doing another industry at the moment, hydrogen. That is
Okay.
expensive, but you know, there'll be learnings from each iteration, and so hopefully by the time this comes along, it'll science, you'd hope.
Crossed.
Any other? I'm conscious that we're getting towards the end, and you all are probably coming to the end of your lunch break as well. Any last question or? All good. Okay. Well, thank you.
Thank you.
Thank you.